Welcome. Again, these tutorials are optional. You don't need to watch them. You don't need to submit an exit ticket unless you need to. Okay? And in this tutorial, I will be solving the practice problem. Uh, so this problem basically it tells you that we have like a gate valve and which control flow. And we know at this gate valve what we get? We get some drop in energy. Yeah, so we get some they cause like a drop in energy. Yeah, and this gate valve it will be conveying some hazardous fluid, but we want to study this gate valve like the drop of energy or pressure drop in due to like in the lab, and we don't want to use this hazardous fluid. We want to use water, yeah, just regular water, and we don't want also to use the actual gate valve with the actual size. We just want to have, because it might not fit the lab, so we want just to have like a smaller one of it, yeah. And so the problem here, it is already defined for you. Remember, like the first step in this uh, problems to find the relevant parameters for your experiment is that like you identify like what are these relevant parameters that control like this physical phenomena. And in this case, these parameters are like dependent and independent variables are already defined for you. So your dependent variable, that's the pressure drop, and your independent values that's given to you as like the valve gate opening. How open, like, so here the valve gate opening would be like 0, for example. Here it would be maximum, yeah. And then the overall depth, so that would be the overall depth here, like from here to here. And the velocity of the fluid, and of course the density and viscosity of the fluid. Remember, this is parameters that we generally use to uh, describe our fluid. Perform dimensionless analysis to obtain the relevant non-dimensional group to scale the model to the prototype. So the model, an actual physical model, an actual valve that looks like this would be in the lab, and the prototype would be the guy, like the one in the, yeah, that we want. So in the lab, we will only have a dimension of 1 to 5. So if this is like, let's say, if this gate valve has an gate opening of or overall depth of like 1 meter, for example, the one we will have in the lab will be only 20 centimeter, yeah. Or if this has like 5 meter, for example, the one we will have in the lab will be only like 1 meter, something like this, yeah. Depending on how big that guy is, yeah. But the actual dimension is not important. We just need to know like the scaling, yeah, like the ratio, yeah. Is built in the fluid. The density and the viscosity of the hazardous fluid. So this is in our prototype is 800 kilogram per meter cube, and this is viscosity is giving like this. And then takes the density and the water. So the density and viscosity of the water, you don't need to check them in tables or anything as we did before. They are just like giving to you. Use the physical model to answer this question. So for a particular opening, when the velocity of the hazard fluid in the prototype is this, what should be the velocity of water in the model for dynamic similarity? So remember, to ensure dynamic similarity, our velocity in the model should scale with the velocity in the prototype. So for this velocity in the prototype, what should be the velocity in our model? So can we calculate this? Yeah. What is the ratio of the quantity of flow Q in the prototype and the model? Yeah. So the ratio. So giving like that now we achieved geometric similarity, we achieved the kinematic similarity, and then we will assume that there's also dynamic similarity. Then what is the ratio of the quantity of flow in the prototype in the model? So for example, if I have, I don't know, 20 meter cube per second in the model, it might be maybe 1.5 or 2 meter cube per second. Sorry, in the prototype, then it would be 1.2 or whatever in the model. It would be, of course, less because this is like the one is this one is like smaller, yeah, and this one is larger. And then finds the pressure drop in the prototype if it is this in the model. So now we measured this pressure drop in the model. What would be the pressure drop in the prototype? So can we do this? Yes, so the first step is that we need to find our dimensionless parameters because now we have 6 variables. We don't want to design an experiment with 6 variables. That is crazy, yeah? How, like if you do the numbering, like the permutation of this, that would be something crazy. But now we know that we can find our dimensionless parameter, and like giving these dimensionless parameters, then we can like design and like represent like the results of this experiment. So choose pertinent variable or parameter and write the functional relationship. So here it is easy because they are already giving to us. Yeah. So basically, what this problem is telling us, it's telling us that the pressure drop, that is a function of what? That is a function of the gate opening. That is a function of the overall depth. That is a function of the flow velocity. That is the function of the fluid property, like density and viscosity. Yeah. So that is easy. So how many variables do we have? How many relevant variables do you have? Like n is equal to what? So n is equal to 1, 2, 3, 4, 5, 6. So n is equal to 6. How many independent dimensions we have? Like so the like m. Remember, like the m is the number of independent dimensions. So here, that is we only have length, we have like m mass, we have time. We don't have like temperature, for example. Yeah, we don't have this. We don't have any other thing. So basically, like so the number of dimension we have is like 3. So that is 3. So n, the number of relevant variable is 6. The number of dimension is 3. What does this mean? This means that we are expecting to have like, so that is like the number of pi. So the number of pi parameters, that is like n minus m, that is equals 3. So you are expecting to get like pi 1, pi 2, and pi 3. In the previous problem like that I showed in the lesson, we only had 2 pi's. Why? Because we only had 5 parameters. We didn't have 6 parameters. But now here we have 3 pi's, 3-dimensionless parameter, because we have 6 parameters. If we have 7 parameters, then this would be like 4. Yeah. Okay. Uh, so that's like choose. Now we want to choose the repeating variables. Yeah. So what is the repeating variables? The repeating variables are the variables that will repeat in this pi 1 and pi 2 and pi 3. Yeah. And the remaining variable would be like the additional variables that I will add that's not repeating here, and I will add to this guy, and this guy. So that would be like the non-repeating variable, or like the additional variable. So remember how to choose like the repeating variable. So the repeating variable, it is always recommended not to choose your dependent variable as your repeating variable. So we can get rid of this guy. Yeah. So we can choose like three of these guys. So it is always recommended to choose like it is not it's required that like that your three repeating variable should include your three dimension mass, length, and time. So let's choose one guy that represents the length, for example. So we can choose the overall depth. Yeah? So I can choose like the overall depth. That would be my first repeating variable. That would be L. Yeah, so the dimension of L. Then we need something that has to do with kinematic or time dependent. So we need to choose another guy that has T, yeah, in it. So I can choose like velocity, then like or viscosity. Of course, I will choose velocity. It's like looks simpler and easier, yeah. So that's velocity, and that will be L T minus one. And then dynamic and like something that's related to mass. So I have to choose like one of these guys, yeah, that is related to mass. So I will either choose density or viscosity. Which one? Density looks easier, yeah. So density, and that would be ml minus 3. So now I have chosen my repeated variables. These are the guys that will appear in each of these three pies. So D, V, and rho, each of these guys will have like these things. And like the remaining one, so the remaining one is pressure. So basically pi 1 will have like D, let me show you here. So pi 1 will have D, V, rho, and pressure, yeah? Pi 2 will have D, V, rho, and height, gate opening, yeah? Pi 3 will have D, V, rho, and what? And viscosity. Yeah, that's why they called repeating variable. And the remaining variable, each of the remaining variable, like this guy will go here, this guy will go here, and this guy will go here. Simple stuff, yeah? So here we did this already. We did this step like of uh, of uh, of finding the number of dimensionless parameter. In that case, like it will be like the pi terms is equal to n minus m. That's like 6 minus 3. That's equal to 3. We already know this, yeah. Uh, uh, we already did this. So now, so here, these are like my, now let's make this a little bit bigger. These are like my repeating variables, yeah, in each pi. Yeah, so here, what does this mean? Like number, so I will have like pi 1, pi 2, and pi 3. Pi 1 will include like this guys and like this guy. Yeah, that would be pi 1. Pi 2 will include this guys and like this guy, the H. Pi 3 will include all these guys, the repeating guys, plus this guy, like the one, the remaining variables. Yeah. Okay, so let's do this. Uh, so do you remember like how we did this? Yeah. So basically, like we will say like pi 1, that is equal to d v, sorry, v dv rho, and my first repeating variable, which is delta p. Delta p. So drop in pressure, yeah. And then remember here, we need to make these this is dimensionless. We know that this guy is dimensionless. So we need to find the power of this guy to make these our left hand side also dimensionless. Yeah. So I want to play with this a, b, like a plus 1 minus 1, b plus 1 minus 1 plus 3, whatever. So I want to keep playing with these powers until I make my right hand term dimensionless as my left hand term, because like here, remember like the dimension of this guy is m minus 0 l to the power of 0 t to the power of 0. It's dimensionless, yeah, so that is equal to 1. That's like my left hand side. So I want to make my right hand side like to, each of these, like this guy has this dimension, this guy has this dimension, this guy has this dimension, this guy has this dimension. So what power do I need to raise this guy to, and this guy to, and this guy to make all these guys on the right hand side dimensionless. That's basically the objective here. Is this clear? Yeah. Okay. If it is still unclear, maybe when we solve it, it will become more clear. But here we do our like repeating variable A, V, B, rho, C. What guy should I put here? Do you know? So that would be the second remaining variable, which is like H, yeah? And then we do like pi 3, my repeating variable A, V, B, rho. And what guy should I put here? That would be my viscosity. So now I have like my 3 pi terms, yeah? Each have like the repeating variable, and each one will have one of the remaining variables. Now, for each of these guys, I mean, these can be solved like these. Each of these is solved independently, yeah. But for each of these guys, I want to find the power that makes the dimensions of the right hand side, like for M, L, and T 0, yeah. Just like the left hand side, yeah. That's basically the how to do it, yeah. So let's start maybe with pi 1, yeah. And maybe I don't know if we need to do like the 3 of them. Actually, the second one is very easy to do. I mean, I will show you like how to do the second one, because the second one is like intuitive actually. So actually, like if you just look at this second guy here, yeah, like how could I make like this second guy dimensionless? I mean, that's like this is you don't here really need any dimensionless analysis. Let me just put this second guy here. Like you don't need to follow like sorry like any systematic steps, yeah, like this systematic steps of the pi theorem. Like you can just put this guy here. This is like d. This is like d to the power a, v to the power, and rho to the power c, and this is like h, yeah. So basically, if you look here, this is dimensionless, yeah. So like you say, like A and B, you know, like how could I make here like this guy dimensionless, yeah? So basically, like for this guy, by inspection, like for this like to be dimensionless, I need to have like d over h, just like pi 2. This is by inspection. That's like the way to make this guy dimensionless is just like to have d over h, yeah. Then that will make this basically this guy dimensionless, because here we have like d, yeah, that's like, and here we have h, yeah. Okay. Is this clear, or should I just like do it like in the systematic way, like I am like confusing you, yeah? D over H or like H over D, whichever, yeah? So basically, like you can, that is how I could make this guy dimensionless, yeah? It's like you just scale like you just find the ratio between these two, yeah. So if this is like unclear to you, I mean, I will like do it like systematically, and then you will find that I'm getting like to the same answer, yeah. But okay, let's do each of these like systematically. So I'm not gonna do the 3 of them because that will like be time consuming. I will maybe just do the first 2, yeah. So let's start with this guy, and I will like make it with you here. So let's say pi 1, yeah. So pi 1, that would be what? So that would be d. So that is equal to L to the power a, yeah. V, that is LT minus 1 to the power of B, yeah, or it might be, yeah, LT minus 1 to the power of B, and then rho, that will be M L minus 3 mass over volume to the power of C, and then delta pressure, that is force over area, and if you don't remember like the dimension of this guy, we can get them from here, from this table. So the pressure, that's M L minus 1 T minus 2, yeah. So M L minus 1 T minus 2, yeah, because that's like force over area, and so okay, so we have like something like this, and here we don't like raise it to any power, yeah. So that is now what do I want to do? What do I want to do? I know like that this guy, like what is the dimensions of this guy, like M, that's M to the power 1, 0, I mean to get 1, L to the power 0 to get 1, and T to the power 0 to get 1. That's how I make like this guy dimensionless, yeah? So this is equal to what? This is equal to my M. So M here, what do I have? So I have like M to the power C, like this guy here. And then I have M plus 1, yeah? Because here M to the power of 1, like here. See, this is M, sorry. This is M to the power of 1, yeah? That is like for the M. For the L, what do I have? So for the L, I have like L to the power of A, have plus L to the power of B, yeah? Minus 3C here, minus 1, yeah? That's what I have for the L. How about the T? What do I have for the T? So for the time, what do I have? I have T minus B, yeah? And I have minus 2, yeah? I have something T to the minus 2. So now let's solve for M, L, and T. Okay, so like how could I make like what value of C, for example, do I need to get like M is equal to 0? So like this is like here, like so this is like 0 is equal to C plus 1. What does this mean? This means that C is equal to minus 1. Yeah. How about like L? Or let's even before L, let's do let's do T first, like T is easier because, yeah. So like T, I have like 0 here, and that is equal to minus B minus 2. So what does this mean? This means that B is equal to minus 2. Yeah, do you agree? So now I know C, I know B. Let's do like the L. Yeah, so the L here, I have like 0 here. That is equal to this guy. Like A plus B minus 3C minus 1. So A is unknown, yeah? Plus B, that's like minus 2. Minus 3C, so that is like minus 1 times minus 3, so that's plus 3. And that is like minus 1, yeah? So what is this? So basically, in that case, I got A is equal to 0 because here that's like minus 3 plus 3 that's equal to 0. So I have C minus 1, A to the power of 0, and B minus 2. So let's write it down, yeah? So here, what do I get here? So I get here like my pi 1, yeah? So that is L. So that's to the power of 0. So it means like I don't have any L here, yeah? And then the B, that's like V to the power here, like see, like the guy to the power of b is sv. So I have, I mean, let me write it down, yeah, so that it would be L, A is 0, so d to the power of 0, yeah, V, P, B, B, V to the power of minus 2, yeah, rho, C, what is C? Like C to the power of minus 1. And then I have my rho B, yeah, so that is basically my pi 1. Like I can even write it like this. I can say like pi 1 is equal to delta my drop in pressure over velocity square times density. Like this is clear. Let me do it here. That is equal to drop in pressure times velocity and density. Yeah, that's like my rho 1. Yeah, do you agree? Can I do the same for rho 2? I mean, just for practice, yeah? It's not boring. I mean, it doesn't hurt, yeah? Uh, and we know already from like just intuitively, we know that rho 2 should be equal to d over h. That's how we can make this thing dimensionless, yeah? Because h, we know this is like length and this is length, so we need to, that's I mean, just intuitively, that's how we should get it. But let's do it systematically and see we will get to the same intuitive results that we have here, or we will get something else, yeah? So let's do it systematically. So I will say like pi 2, that is equal to d, so that is like length, yeah, to the power of a, that is equal to v lt minus 1 to the power of b. I'm just copying from above. And rho, that is ml minus 3 to the power of c. And what do I have here? I have like L, yeah, because that is my drop in pressure, and that is L, yeah. Let's just do it systematically as we did before. So here we have m to the power 0, L to the power 0, t to the power 0. I mean, these things are really easy and fun. Yeah, you can just like really, it's kind of just relaxing to sit and do this simple problem. Yeah. Okay. So here, m to the power c. Yeah. Do I have any other m? No, I don't. Then I have L to the power A plus B minus 3C. Yeah. So here, this is like M, I only have it here. Here, L is A plus B minus 3C. Would I have another one? Plus 1 here. So here I have an L. I have a guy hiding here. Yeah, plus 1. So pay attention, like make sure not to miss anything. I was about to miss this one. And then you have T, that would be like minus B. And what else do I have? Yeah. So you see here, that need to be 0 and that need to be 0. Yeah. You can already see it's already started to appear. So like if you look at M, so basically like you have 0 is equal to C. If you look at T here, you have 0 is equal to minus B. So here C is equal to 0. And here you get B is equal to 0. That's exactly what we expected, yeah? And we only expect length. And guess what A will be equal to 1? What? Yeah? So can you guess uh, uh, what A here should be equal to what? I mean, we can do it. Okay, so we can say like here's this is equal to A plus B plus like 0 minus 0 plus 1. Yeah. So what did I get? I got like A is equal to minus 1. Yeah. Let me just delete this. Yeah. So that's like all like this is A plus this is 0, this is 0, A plus 1. So here I got like A is equal to minus 1. Yeah. And that's it. Yeah. So can we write our pi 2? Yes, we can write our pi 2. So pi 2, remember what this guy was? So here, that is like so pi 2, that is like the L to the power A, that's like D to the power A, and A is equal to minus 1. V to the power of 0, that's exactly what we expected. Rho to the power of 0, because that's like to the power P and C. And then L, which is the other guy like H. So I got like pi 2 is equal to H over D. Or D over H, yeah, doesn't matter. Or D over H. Remember, this is all dimensionless. H over D or D over H, yeah. Exactly like what we expected, like what we did here intuitively, we just did here systematically. Remember, I told you like this pi theorem, this is just a systematic way for what we are already will do intuitively anyway, yeah. And then you can do the same for pi 3. I mean, like these steps are repeating, so I don't want to like make this video long, but if you like repeated the same steps, you will get something like you will get. So try to do this on your own. So like when I did this on my own, I got like for pi 3, like try to do this on your own. I got like A is equal to minus 1. I got B is equal to minus 1, and I got C is equal to minus 1. Then I got like, so try to do it on your own and see if you will get the same thing. Yeah. B is equal to D minus 1, V, sorry, V minus 1, rho minus 1, and mu. Yeah. So that is this guy here. Yeah. Okay. So basically, what is the next step? Like, do we have a next step? Oh, we have a next step here. So the next step is that we write the dimensional analysis result. Yeah. The dimensional analysis results, like what we got above, we got like rho 1, that's equal to V square rho minus 1 delta B. We got like rho 2, that is like equal to H D minus 1. Yeah. Uh, and we got actually it was like D minus 1 over H. Yeah. Just keep it like this. Yeah. Keep is a non-repeating variable. And then here we got like D minus 1. We got V minus 1. We got like rho minus 1. And we got mu. Yeah. So that's what we have here. Does this guy look familiar? Yeah. Have we seen this guy before? Yeah. This guy here. Does this look familiar? Let me show you. Like this guy. Like mu over d v rho. Mu over d, sorry, d v rho. Yeah. Actually, this is my Reynolds number. So I will just say like is equal to the rho 3. You can give it by, or it really doesn't matter, yeah, prime, but so I just like invert this guy. I would like to invert this guy. So I would like, because it's really dimensionless, d v rho over mu. Yeah. And this is basically like our Reynolds number. Yeah. So what do we have here? So we have here, like for this guy, like rho 1, we have the drop of pressure over rho v square for our pi2, we have h over d, and for our pi3, we have our Reynolds number, dv rho over mu. Yeah, so basically that's what we have here. Let me just delete this guy here. So, and basically, like this is our dependent variable. Like pi1 contain our dependent variable, and pi2 and pi3 contain our like independent variables. Like see, like 1, 2, 3, 4, 5, and here's 1. Yeah. So basically, what I can do, can I also write something like this, like pi1 equal, it's a function of pi2 and pi3. Can I do this? Yes, because here pi1 contain my dependent variable, pi2 and pi3 contain my 5 independent variable. So can I just say something like this? Delta B, drop in pressure, rho V square. That's like a function of what? Of H over D and rho V D mu. Can I just write something like this? So basically, this is the results of like this analysis. Yeah. So we have something. We have like something that looks like this. Yeah. And now, do you remember like giving like we have geometric similarity, same shape. We have uh, giving like the geometric similarity and kinematic similarity. So dynamic similarity would require that all non-dimensional group be the same in the model and the prototype. So remember, so like I have here, this is like all non-dimensional groups. I have like 3 non-dimensional group or 3 non-dimensional parameter pi1, pi2, pi3. And the principle of similarity states that the rho uh, like let's say how to write this. Okay, so for example, yeah, I have like rho 1 pi1 is equal is a function of like pi2 pi3 to pi n. Yeah. So basically, the laws of similarity say if pi 1 m is equal to pi 1 b, like here, like this guy here, yeah, uh, here, then pi 2 model is equal to pi 2 prototype, and then pi 3 model would be equal to pi 3 prototype. Yeah. So if like these guys are the same because of the laws of similarity, then these guys will be the same. Actually, this is a great, yeah. Isn't this great? Because now I can say pi 1, yeah, that is equal delta B, okay, over rho V square in my model. Like all these guys in my model will be equal to delta B rho V square in my prototype. Yeah. Similarly, like pi 2, like h over d in my model will be equal to h over d in my prototype. Similarly, rho vd over mu in my model would be equal to rho vd over mu in my prototype. And what can we learn from this? So basically, we can like just arrange the term. Like we can find this velocity and like the ratio between the velocity in the model and the velocity, for example, in the velocity in the model here and the velocity in the prototype. So that's like the prototype. So I can say, like, let me do this. So I can say like rho model v model d model over mu model, that is equal rho prototype v prototype d prototype and mu prototype. Okay. So can I just like put, I want to see like, I want to get like v prototype over v model. I want to get like this ratio. So that would be equal to what? That would be equal to rho model v model, no, sorry, rho model d model, okay, mu prototype. I just bring this guy here over uh, rho prototype. I just bring this guy here, v prototype and mu model. Wow. I mean, isn't this something good? Yeah. So this is something good here. We have a relationship. Sorry, we have a relationship between like the ratio between the velocity in the model and the velocity in the prototype. So what we have here. Sorry, this is the model, yeah, over the prototype. It's this is known, this is known, this is known, this is known, so we can, if we know one of these, we can find the other, yeah, or if we want to, like, depending on the problem we have, but we can find similar relationship. So can we find, for example, like a relationship for Q, like Q prototype over Q model? Can we find this relationship? That requires a little bit of thinking, because Q, what's Q? Remember, like Q flow, we've seen this before, like that's velocity time area, yeah? Because velocity is this L over T area, that's L squared, you get Q, yeah? So basically, that would be like velocity of the prototype time area of the prototype over velocity of the model times the area of the model, yeah? And area, remember, like is pi, like d square, for example, over 4. Uh, remember, so this will go with this, and basically you get like, because this guy will go with this guy, so you get like v p d, like here, d prototype square, or this is like the area, yeah, area, because remember, like area is pi r square, yeah, and r, just show you this slide in case you don't know what I'm doing. R is d over 2, yeah, square. So the area will be like d square over 4, yeah, just in case you don't remember or don't know, yeah. So so here that would be v. So I can, so like, you know what I did here, yeah. So like what I did here, let me do it for you step by step. Yeah, so here that would be like this is the diameter. Sorry, this is like diameter square of the prototype over 4 v v here, v model by diameter of the model square over 4. So basically, like this guy will go with this guy will go with this guy. So here I get like V P D P square over V model D model square. Yeah, do you agree? Or alternatively, I can just write it like this, like V P over V M time dp over like this ratio dm and like square. Yeah. Can I do this? So that would be, so let me erase, here's this guy. So I have my second relationship. Well, I'm getting now everything. Q P is equal to QM. Yeah. Delete this guy here. So I have like my second relationship here. So I have like, this is my first relationship. This is my second relationship. What all else I'm interested in? I'm interested in like the drop in pressure. So the drop in pressure, we already have like this guy for it. Yeah. So the drop in pressure, we can do this guy. So we can get it from here, from this guy. So basically I'm gonna do it here. I can do it here. So I can say like drop in pressure model, rho model, v square model is equal, like I'm using this guy here, drop in pressure prototype over rho prototype over v square prototype. Yeah. And I want to find like the d p over d m. Yeah. That's what I want to find. So what will that be? That would be like rho b v square p over rho m v square m, which I could also write it as drop and pressure for model is equal to rho prototype over rho model, v prototype over v model, and then I take this like, square. Yeah, do you agree? Okay, so now we have what we have. Yeah, we have this, guys. So now what is this problem telling us? Yeah, so let's just see, let's read here. What is this thing is like telling us, and what does it need from us? Yeah, so basically what this thing is telling us is it is telling us a 1 to 5 scale model is built. So now we have a useful piece of information is like, so we know that like D model over D prototype is equal to 1 over 5. So this is giving, yeah. One is built to determine the pressure drop across the valve with water as the flowing fluid. So we don't want to use the hazard material. The density and viscosity of the hazard fluids, we are giving like rho. We are giving here rho. Prototype is 800 kilogram per meter. I'm not gonna write the units here because these are the same units. So that's like, if I look at this guy and this guy, these are the same units. Yeah, if I look at this guy and this guy, these are the same units. So, and I know they will cancel. Yeah, so I'm not gonna write it just because I'm lazy. Yeah. Okay, and then row model, that is like 1000. And because, not just because I'm lazy, just because you don't really need them. Like if you understand dimensional analysis, and that like as long as these units are consistent, yeah. If these units are not consistent, you need to make them consistent, yeah. But as long as they are consistent, then this is like, this is 5 here, yeah. So we are giving this, and like we are giving the viscosity of this guy is this is like the viscosity of the prototype is this guy here, like 10 to the power 2 times 10 to the power minus 3, yeah? And the viscosity of the model, that's like of water, that's like 1 to 10 to the power minus 3. So again, do we need this guy? No, this is like 10 to the power minus 3, 10 to the power minus 3. Yeah, you can just delete this all. Yeah, just 2 to 1. Yeah, because that's all you need. Here you can do the same. Here you can just say like 8 to 10. Yeah, 2 to 1. Yeah, 1 to 5. You see like where I'm getting at? Yeah. Not, but I mean, you don't have to do this, but I'm just like showing you. Yeah. So basically, use the physical model to answer this question. Use the physical model to answer this question. For a particular opening when the velocity of the hazard fluid in the prototype is, so we are giving like V prototype is like 3 meter per second. Let me get this in 3 meter per second because like my final answer would be like a meter per second. So I would like to preserve this information. What should be the velocity of the water in the model to ensure like dynamic similarity? So now we are saying like what is the velocity of the model? Like, can we do this? Yes, of course we can do this because here we have like this, let's say, we have this nice relationship here. Like you see here's this guy. So basically that's my relationship like VP over VM. That is equal rho model over rho P, sorry, prototype, time D model over D prototype, time U prototype over U model. Yeah, that's what we have. That's the relationship here. So can we find like this guy? Yes, we can find this guy because uh, basically like, I mean, let's just substitute what we have here. So we have like this guy is equal to 3 over Vm. What is this? The ratio of this uh, guy to this guy, model to this guy. So that's like 10 to 8. Yeah. And D, what is the ratio of D model over this guy? That's like 1 to 5. Yeah. And what's the ratio of this mu prototype to mu model? So that's like prototype to models. That's like 2 to 1. Yeah. So if we did this, like, let's just do this guy. So we can remove this guy and put like 2 here. Yeah, do you agree? We can remove this guy, yeah, and put like 4 here. And then we can remove like this guy. We can remove these 2 guys and put 1 over 2 here. Yeah, do you agree? So this will mean that Vm is equal to 6 meter per second. Yeah, that's That's what this is. So what does this mean? So it means that like in our uh, small scale model to ensure dynamic similarity, yeah, where like this, so that we can calculate like this drop of pressure, we need to run our model at like 6 meter per second, yeah. Like flow need to be like 6 meter per second to ensure dynamic similarity so that we can compare the pressure drop, yeah, between like the model and the prototype. So what else it's asking us to do here, yeah? So again, this is like the same problem. Use the physical model to answer this question. Like the physical model to answer, I'm repeating it. What is the ratio of the quantity of Q in the model and the prototype? So what is Q model versus Q prototype? I mean, that shouldn't be difficult. Like we have this relationship already, yeah? So we have this relationship already here. So, I mean, I have like QP over QM. That is equal to VP over VM times dP over dm. That is, oops, that's like square here. Yeah, that's too large. Yeah, me just write it. Q P over QM, that is equal to VP over VM time dP over dm square. So let's look at this problem here, yeah? So we need this ratio like Q uh, P over QM, yeah? And that would be like VP over VM, like, so that is like, we have like, this is 3 and this is 6, yeah? We just got this guy here, like, so that's like, we know that, oops, what's going on here? Just know that this is like 3, 2, 6, yeah? And then dP over dm, we know that we already have this guy here. We have dm over dp, which is 1 over 5. So dp over dm, that would be like 5 over 1. Yeah, and that's square. So that will give us, that would be like, so that's like 1 here over 2. So we can remove this. So we can get like here 25 over 2. Yeah, so this basically ratio is like 25 over 2. So if I have like 2 unit of this flow in the model, that will correspond to 25 unit in the prototype, which makes sense because this model is much smaller. Yeah. That's exactly what we expect, that like this is like would be here. So you see here is, and you see this like non-linearity already. Yeah. And because you have all this square, so that's why you get this like non-linearity. So it's not like 1-to-1, like this is 1/5 of this side. So if I have like 1 of these units here, I will have like 5 of these units here. No, it's not like this. But it's like you see this, like you have this non-linearity, and also it's a function of velocity. And that's why we need exactly to do dimensional analysis. It's not like, oh, I got this in my model. So in my prototype, like my model is 1/5 the side of my prototype. I will just multiply by 5 or divide by 5. No, it's not that simple. Yeah, it's not that you just multiply by 5 or divide by 5, because this is how the scale between your model and prototype. You need to account for this relationship and like the like non-linearity. Okay. Okay, are we done or not yet? Well, one more question. So the last question is like about like the drop in pressure. Yeah. So the last question is about the drop in pressure, and we have like this uh, remember equation for the drop in pressure. Let's do it. Let's go up. Oops. What's going on? What's going on here? So we have this equation. Let's just see. So that equation in the drop in pressure, basically it tells you like the dP over dm, that's rho p over rho m, vp over vm square. Yeah, so let's do it. Yeah, so that's like dP over pm, that is like rho p over rho m, vp over vm square. Yeah, we know already, we know this already. So we know like this guy is like the prototype, that's 8 and that's like 210. And we know that in the prototype that's like 3 to 6. We know this is like 3 to 6, yeah. And this is like square. So now it is telling us, okay, take the kinematic viscosity, blah, blah, blah. Find the pressure drop in the prototype if it is in the model. So this is what we measured in the model. So this is how much pressure drop we have in our model. What will be the pressure drop in our, this is in kilopascal. What would be our, the pressure drop in our prototype? So like that is the P pressure drop, and this is like would be like 60, yeah. So if we did this, it's like 4/5, and if we did this is like here 1/2 square, yeah. So basically like this guy will go with this guy, so we will get like 1/5, yeah. Uh, yeah, you will get, yeah, 1/5, yeah. And then so we will have like dp is equal to what's this? Yeah, 160 divided by 5. Yeah, so you just multiply like this guy by here, so that's like 60 divided by 5, and that will be equal to 12. Yeah, 60 divided by 5, that give you 12 kilo Pascal. Yeah. So basically, okay, uh, delta V prototype is equal to 12 kilo Pascal. Yeah, 12 kilo Pascal. Okay, so this is in the model and this is the prototype. Okay. Okay, I think that's conclude. Like you have a homework, like your homework is very similar. Like you will use this equation to calculate like this number. You will like use this equation to calculate like this ratio, and you will use this equation to calculate this. And then you have to answer some question to see like do you understand really dimension this dimensionless parameter or not. So the first question that's conceptual, just to see if you understand the main concepts or you didn't get it. Like if you understand that like these things are dimensionless, so it doesn't matter which is the numerator and which is in the denominator because they will remain dimensionless. It doesn't matter which is your pi 1 and pi 2 because they are all like doesn't matter like which is pi 2 pi 3 because pi 2 and pi 3 because you can switch them. I mean pi 2 could be your pi 3 and pi 3 or your pi 2, yeah, and pi whatever because these are all dimensionless. Yeah. So I think that's all for this like tutorial. I think it's a long tutorial. Let's see. Yes, it went like over an hour, but that's okay. Like that's the idea of this tutorial is just to go very slowly for the student who are still like learning this material because I know some of students these things are trivial like I mean they can just they don't need this but other students they might need uh, additional assistant and so that they learn, yeah, because if you know everything I mean that's why you are here. Like if you don't know these things you're here to learn them, and if you already know these things please be patient because it's not gonna be like basic like this. Like I will be also covering like at more advanced material and more graduate level type of material. Yeah, so please be patient. Yeah. Okay. Okay. Thank you and see you in the next video.